In our first lesson, we're going to take a look at quadratic functions. Let's begin by looking at what a polynomial function is. We've already seen polynomial expressions. These are expressions that involve powers of x's. So, for example, 4x to the 4 minus 17x plus 3. So here we have a polynomial expression because it has x's and powers of x's all related together. And what we can do is we can define a function out of this expression. So here we can just define a function f of x using this polynomial expression. The nice thing about polynomial functions is that their domain is all of the real numbers. That means any x value is going to be allowed as input. Of course, the particular function f of x here is just one example of the infinite number of polynomial functions that we might work with. The polynomial functions that we want to talk about in this chapter first are called quadratic functions. Now we've already seen quadratic expressions. These are polynomial expressions where the degree is equal to 2. So, for example, one quadratic function might look like 3x squared minus 2x plus 1. When I say degree 2, remember that that means this is the highest power of the variable x in our polynomial function. And just like other polynomial functions, because this is just a special polynomial function of degree 2, the domain of this function is all real numbers. And of course that's true for any quadratic function. A quadratic function is always going to have a domain x's in R. One thing that I think is important for us to talk about for quadratic functions is what we call vertex form. A quadratic function could be given in vertex form, and if it is, then we can easily find the maximum or minimum value of our parabola. So here I have a general vertex form for a quadratic function, a times x minus h all squared plus k. Now we need to look to the value of a first. The value of a is going to indicate to us whether or not our parabola opens up or it opens down. The other two important values here are h and k. H and k are going to indicate either the maximum or the minimum value of our parabola. If a happens to be greater than 0, that means our parabola opens up, and hk is going to be the ordered pair for our minimum. If a happens to be a negative number or less than 0, then our parabola opens downwards, and hk is an ordered pair that describes the maximum of our parabola. So let's take a look at an example of how we can use this information in vertex form to give a rough sketch of what a parabola might look like on the xy plane. Given the following quadratic function, negative 3 times x plus 2 squared minus 5, let's try to give a rough sketch of what this one looks like. Now remember, where we want to start is we want to start at the value of a, since this is in vertex form. Our value of a is less than 0. That means our parabola is going to be opening down. After we have this information, we move over to the other information we need, and that's the values of h and k. So now we can create an ordered pair. Our ordered pair is going to be negative 2, negative 5. Be careful here, because the value of h, or the value that's inside of our brackets here, is always going to have the opposite sign in our ordered pair. Since our value of a is less than 0, that tells us negative 2, negative 5 must be a maximum. So if we go and plot this point, negative 2, negative 5, maybe it's somewhere around here. And our parabola opens downwards. So this is a maximum point. So we have a parabola that looks something like this. In our last example, I want to work through a procedure to show you how to find the x and y intercepts for a quadratic function. Now the process to do this is just the same as we've seen before. If we would like to find the x-intercepts, we're going to set y equals to 0. And if we want to find the y-intercepts, we're going to set x is equal to 0. So remembering that we can substitute f of x here with the variable y, if that helps you remember, let's go ahead and find the y-intercepts. we are going to set x is equal to 0. So we start with our quadratic function, y is equal to 6x squared minus 15x minus 21. And we can go ahead and make the substitution. X is equal to 0, so here we'll get 0 squared minus 15 times 0 minus 21. Or we're going to get y is equal to 0 minus 21. So we can conclude here that the y-intercept is given as the ordered pair 0, negative 21. Let's work through this procedure for the x-intercepts, where we're going to assume that y is equal to 0. If we make our substitution, y is equal to 0, we're going to get 0 is equal to 6x squared minus 15x minus 21. And the only way for us to solve this equation is for us to factor the right-hand side. So in red here, I'm going to try to use the trial factor method to try to figure out how to factor this quadratic expression. Remember that we want two values that are going to give us a sum of negative 15. So 15 is our target here. I'm going to look first at 1, 6, 3, and 7. I'm really going to probably ignore the 21 because it's probably going to be too big for us to really use that particular trial factor. So 1 times 3 is 3, 6 times 7 is 42. The sum or difference there isn't going to get us to 15. So let's move on down and let's try using the 2 and the 3 and the 3 and the 7 and see if that works. 2 times 3 is 6, 3 times 7 is 21. And if we do 21 minus 6, that's going to get us our 15. So I'm going to attempt to use these two factors, 2, 3, 3, 7, to try to factor this quadratic. So remember, it's this 2 and 3 that give us the 6x squared. So those are going to be our leading terms here. And then the 7 and the 3 are going to go in backwards in our trial factors. Now we just have to figure out what our sign is. We need a negative 21 and a negative 15. So one of these numbers has to be positive and one of them has to be negative. Well, let's start out with this 7 times 3. This is equal to 21. Let's start out with a negative 21 x's and then add 6 to that. That should give us our negative 15 that we need. Now that we have everything factored up, we can use our factors here to solve for x. This factor here is going to yield 2x minus 7 is equal to 0. And if we solve for x, we're going to get x is equal to 7 over 2. Our second factor tells us 3x plus 3 must equal to 0. And if we solve for x here, we're going to get x is equal to negative 3 over 3, or x is equal to negative 1. That means our parabola actually has two x-intercepts. The first x-intercept has x-coordinate 7 over 2, and our second x-intercept has x-coordinate negative 1. Of course, the y-coordinates here are both equal to 0. That was the assumption that we started with. All right, my little epsilons, stay positive.